We have one more approximation for area in the plane. I know that I said when I did the videos for the definite integral that we would be doing fundamental theorem, but I want to cover the trapezoid rule first because it is another approximation for area in the plane. Riemann used areas of rectangles to approximate the area trapped in the plane between a function and its horizontal axis. The trapezoid rule, or the trapezoid sum, it could equivalently be written as the trapezoid sum, can also approximate area in the plane. And hopefully you can see now we don't have rectangles in the plane, we have trapezoids. Now, we're used to trapezoids from geometry looking like this, and the area of a trapezoid was 1/2 the height of the trapezoid, which was this horizontal distance in between the bases. It was 1/2 of the height times the sum of the bases of the trapezoid. Our trapezoids are going to be labeled like this. We're just like we turned our rectangles kind of up on edge. Our trapezoids are going to have, you know, these flat sides here, and instead of our height being this distance, we're going to call it width, and then we're going to have the sum of our heights. We'll have height 1 and height 2. All right, so we have all these trapezoids in the plane. So our area, when we use area of a trapezoid from geometry, what we are calling h here, we're calling w here. So ours is 1/2 the width times the sum of the heights. And let's say we look at this trapezoid right here, if I can draw a straight line. And so this would be height 1, and this would be height 2, and this would be the width. So hopefully you get the idea of what your trapezoids are going to look like when you're doing the trapezoid sum. So let's work a couple of examples. I want to kind of point some things out for you, and then you'll be responsible for using not only Riemann sums to approximate area, but trapezoid sums or the trapezoid rule as well. So given the function 1/8 x squared plus 1 over the interval from x equals 0 to x equals 4, we're told to find or approximate the area from 0 to 4 underneath our function with respect to x. And we're going to use the trapezoid rule or a trapezoid sum to approximate that area. So let's label some things here. Here are our widths. There's width 1, width 2, width 3, and width 4. We can clearly see that our widths are all 1 unit long. But just like we did for Riemann sums, the widths here are found the same. If they're all the same, we take the right endpoint minus the left endpoint, and we divide by the number of trapezoids that we have, and that's going to give us our width. So our area, our accumulated area here, is going to be approximated using a trapezoid sum with standard widths of 1, and then we're going to just add up all of our heights. So here's height 1 and height 2, height 3 and height 4, and height 5. That'll be a good way to label those. So the area of trapezoid 1 is 1/2 the width, which we said was 1, times the sum of the heights, height 1 plus height 2. Well, those heights come from our function. It's the output of the function at these input values. So height 1, we can see here, is 1, but what we're going to do is we're going to plug that x value into our function. So height 1 is 1/8 times 0 squared plus 1 plus height 2, which is going to be 1/8. The input value here now for height 2 is x equal 1, right? So there's height 1 plus height 2. And we're going to have times the width because we could distribute that through there, right? And we would have, oh, I forgot my 1/2. Got to watch me. 1/2 the width times the sum of the heights. Now I'm going to add the next two heights together. Now we're at trapezoid 2. So I have height 2 plus height 3. So height 2 we said was 1/8, plugging in this value for x, 1 squared plus 1. We add to that height 3, which comes from an x value of 2. So 1/8 times 2 squared plus 1. And now that is height 2 plus height 3. And then we just continue. We'll need height 3 plus height 4. 1/8 times height 3 comes from an x value of 2. Height 4 comes from an x value of 3. And there's the sum of 3 and height 4. This is height 3, there's height 4. It's going to be height 4, height 5. So 1/8, height 4 came from x equal 3, and then height 5 is at x equal 4. So there are all of our heights. There is the trapezoid sum, or the trapezoid rule, that approximates the area trapped in the plane. Now I want you to notice something. Here's height 1, here's height 2, height 3, so come on, do it right, height 2, height 3, height 3, height 4, height 4, and height 5. Notice that all of the interior heights, and by interior I mean not an endpoint, all of the interior heights, height 2, height 3, and height 4, are in this sum twice. What we've done here is we've done 1/2 the widths times the output, or the height, at the left endpoint once, the height or the output of the function at all interior points twice, and the height at the right endpoint once. So there's even a more concise way that we could write this that would probably be easier, and that way we're not writing these things twice because we just want 2 of those. So here I've done it, and you can see here's height 2 and height 3 and so forth. You can see that those are in there twice. So all interior heights are used twice. So when we get over here to the trapezoid sum, and we say that the trapezoid, that should be an approximation. Sorry about that. The area trapped in the plane, starting at A and stopping at B, is approximately 1/2 the change in x. And remember, the change in x are what we call the width. It's the output of our function one time at the left endpoint. That's what x naught means. That's where we start. We could say that that was at A. We could say that was f of a as well as f of x naught. So it's the output at the left endpoint once. It is twice the output of all interior points, and it is the output once of the right endpoint. So when we look at this, this is just kind of like the example that we did a while ago. And again, our widths are the right endpoint minus the left endpoint divided by the number of trapezoids. So let's do this example here. Use the trapezoid rule with n equal 5, so we want 5 trapezoids, to approximate this area in the plane. Again, just like with our Riemann sums, it might be helpful, it will be helpful, to draw the bottom of our trapezoids. So we're starting at 1, we're stopping at 2. So 1 trapezoid, 2 trapezoids, 3 trapezoids, 4 trapezoids. So there we go. Our widths are the right endpoint minus the left endpoint divided by the number of trapezoids. So our widths are all now 1/5. So if we start at 1, which we could consider 5/5, then this x value is 6/5. There's 7/5, 8/5, and 9/5. So that's where we're going to get our heights. Remember, height 1 is here, height 2, height 3, height 4, height 5, and height 6. So the integral from 1 up to 2, 1 over x dx, is approximately 1/2 the widths, which we said were 1/5, times height 1, which comes from plugging this value into the function. Our function is 1 over x, so that's 1 over 1 once. Height 2 twice, that's 1 over 6/5. Height 3 twice, That's 1 over 7/5. Height 4 twice, 1 over 8/5. The next height twice as well, 1 over 9/5. And that right end point, we want the height only once. So see how simple and easy that is? And there we are. There is an approximation using areas of trapezoids for the area trapped in the plane from 1 to 2 underneath this function. All right, so that's it. That was a very simple, sweet, and short video, one video for this lesson. So practice some trapezoid rule examples and then come to class next time and we'll do some homework problems over it.